geometry students. Today we're going to be talking all about transformations. I'm sure that you have a base knowledge of what the word transformation means. You know, some people make transformations through the years, but I wouldn't know anything about that. So let's talk about transformations in geometry. We have some key words here like rotation, translation, dilation, or you could do a reflection like this across a line of symmetry. Let's check them out. Alright, here are the standards that we will be addressing today. The big one here is going to be to represent transformation. So we're going to be talking about definitions of all kinds of transformations and then continuously addressing this leap evidence statement here. Okay, so our first objective set comes from Unit 1, Lesson 6. We're going to classify a transformation given the pre-image and image, identify a center of rotation, identify a line of reflection, and identify a translation vector. So first let's talk about what transformations are. So a transformation is a change. It's a change in the shape. The original figure is called a pre-image, and then the figure after transformation is called the image. So there are two kinds of transformations, two categories or groups. One is isometric, and then another one is non-isometric. So isometrics create congruent images. They are the same size and the same shape. These are also called rigid motions. Okay? Non-isometric creates non-congruent yet similar images. So only one of the transformations is non-isometric, and that's a dilation. The other transformations, translation, reflection, and rotation, are all isometric. They create congruent shapes. So let's talk about the first one, reflections. A reflection is a transformation that flips the figure across a line. That's the main goal of it. If that helps you remember, is that a reflection is flipping. Key word. Okay. It creates a mirror image. You also have a line of reflection when you flip that image. So if we look down here at this picture, this is a shape that actually has a line of symmetry drawn through it. If I were to fold that shape over this line here, then the shape would land on top of itself. But you could also flip the shape around and you still get the same shape. So this can be considered a line of reflection. Now, a line segment connecting a point and its image is perpendicular to the line of reflection, and the distance from the pre-image to the line of reflection is the same as the distance from its image to the line of reflection. Very wordy. All of that means is, if this is a point on the pre-image, and this down here is a point on the image, if we draw a line segment that is perpendicular to the line of reflection, and same with the image point, so both of these are perpendicular, then what that means is that both of those segments are congruent, so that the points are the same distance from the line of reflection. Okay, so let's look at this example. Is the line of reflection L, M, or N? So you can see we have L labeled here, that's this dotted line. M labeled here, that's this dotted line. And then N is labeled here. So we want to know what is the line of reflection for this shape. Kind of looks like a cent sign. Okay, so if we think about it, does it reflect over L? Yes, it does. L is what it reflects over. we can see that if we compared these points here, they are the same distance away from each intersection perpendicular with L. So these segments are congruent and these segments are congruent. Okay, and then you can test out the other lines to show that they don't work by sketching in your perpendicular lines. So M, if we were to draw from this point, a perpendicular line to M would be about there. And then a perpendicular line to M would be about here. So they look to be about the same distance. However, they do not meet up in the same place. So that's another reason why they're not going to be perpendicular. Okay, and then as far as N goes, well, N just doesn't work at all. If we were to draw those lines, you've got this one here, and this one goes there, so they don't connect at all. Okay, so rotations are turns. Okay, a rotation turns a figure a certain number of degrees, and that is called the angle of rotation. And then we know that it will be around a central point called the center of rotation. So you need direction and you need magnitude. That's how many degrees you're going to be turning. Okay. So if we take this compass and we turn it this direction, then we have rotated it to this second image. So taking a look at this image, we can see that the pre-image is the top arrow and the image is the bottom arrow. We want to decide what is the center of rotation. So you can kind of tell from the diagram, because it's marked, that the center of rotation is going to be this blue dot here, the bottom right corner of the arrow. So if you were to put a thumbtack right there on the arrow and turn it, you would end up with the arrow that is on the bottom. Okay, let's try another one. What is the center of rotation for the image and pre-image of the A? V is much too close to A. If it rotated around the point V, everything would be the same distance from V at all times. So that means that a rotation would have to be somewhere around here. And even then I kind of sketched it a little bad, but that radius is much too small. Okay, let's look at point U. So if we kind of look at just the radius, basically, of the circle that would be made with the common points on the letter A, they're kind of close. They look like they could be congruent. But if we think about this letter A turning around, okay, so if the letter A turns to about here, if it makes 180 degrees, it's going to be oriented this direction. So by the time it gets all the way down here to the bottom, it's going to be oriented upside down. So that's the big problem with U as the center of rotation. So that leaves, what's left for us is T, and that one is going to be correct. If we kind of connect the radius, we can see that those 2 points are looking like they're congruent. And then when it turns around, if it just turns that, looks about 90 degrees, then the orientation is going to be correct. It's going to turn to face that side. All right, and the last one we're going to talk about is translations. When you translate a figure, you slide it on a straight path without rotating or reflecting. So this star was translated to this star. You need a distance and you need a direction. So 2 down, 3 right. something like that. This is considered a vector. This blue arrow is, because it gives you direction and distance. So which translation vector, R, Q, or S, was used for the pair of figures? So we can see that we have two hearts here. We aren't told which one is the image and which one is the pre-image. So we have to figure out which vector most closely follows the path that will connect these two hearts. So we can eliminate S because we can see that though that arrow doesn't go down like that from either one of the hearts. So then we're left with R and Q. So Q is going to be the one that gives us the most accurate angle. R is pointed a little too sharply. So Q is our correct answer. Alright, let's move on to our next set of objectives from Unit 1, Lesson 7. Describe the rotations that map a given polygon onto itself, and determine if a figure has rotational symmetry. So before we talk about rotational symmetry, let's just touch on reflection symmetry. And that is just a line that is drawn through a figure so that one side is a reflection of the image on the opposite side, and that will give us our line of symmetry or an axis of symmetry. So you can see that this pentagon, because it is a regular pentagon, meaning all sides and angles are congruent, then it has several lines of symmetry where you could fold that pentagon in half and it would land on top of itself. So now rotational symmetry is very similar. We are still talking about it landing on top of itself, except now it is after being turned. So if we can rotate about a point, most likely it's going to be the center. You can rotate less than one full turn and land on top of itself, then we consider that shape to have rotational symmetry. Because every object, even this crazy smiley face down here, can be rotated 360 degrees and land back on top of itself. So it is only considered to have rotational symmetry if it can turn less than 360 degrees. So let's look at what some of those are going to look like. So does this square have rotational symmetry? So if I were to put a center of rotation in the center of the square, which is about there, just about, and if I were to turn the square around, I could turn it 90 degrees and it would land right on top of itself. So yes, the square does have rotational symmetry. What about this triangle? Does it have rotational symmetry? So this triangle does not have rotational symmetry. All of its side lengths are different. And so for me to rotate it and for it to land on top of itself, it would have to go a full 360 degrees all the way around. Okay, so let's talk about angle of rotation. So this applies to what we like to call regular polygons, okay? That they are all regular. We can name a polygon by its number of sides, so you can review this list of names here. And if we want to find out how many degrees it will take to rotate a shape on top of itself, given that it is regular, then we just simply use the formula in the red cloud. We know that 360 degrees is a full circle, so n is going to represent the number of sides. And that'll tell you how many degrees it needs to turn. 360 divided by the number of sides will land a regular polygon back on top of itself. So let's put that in action. What is the measure of the angle of rotation for the regular polygon? Well, let's start with the formula. The measure of the angle of rotation is 360 degrees divided by the number of sides. So since n represents the number of sides, let's count how many sides are on this shape. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So, do you remember what that is called? It's called a nonagon. So 360 divided by 9, remember you can just do 36 divided by 9, which gives you 4, and then bring down your 0. So if I rotate this shape 40 degrees, it will land on top of itself. And that is all for that objective today.